Welcome back, everyone. This is our second lecture for week 4 on the theory of, the scientific theories and concepts behind our current understanding of climate science, and a lot of that has to do with, the way that we parameterized and thought about energy budgets. So, the energy provided by the sun and how that translates into um, energy absorbed and emitted within the Earth and outside of the Earth and within the atmosphere. So first fun fact for the day. I find that, most of us in the US, we tend to only look at maps of the United States. So I thought it would be fun to look at one from Europe. And my buddy Brian had just created this one um, within the last week. And it's good. I mean, it kind of gives us a sense of, okay, what's happening elsewhere in the world, right? We see those global maps and we see a lot of red, and then we see, the US, we see reds and blues, and we're not totally sure, what the patterns are. So it's kind of good to go and see, what other parts of the or world are experiencing. And more importantly, this helps us understand, people's perceptions and attitudes towards these things. So I thought it was particularly fascinating that, basically across Europe over the last 60 years, and this is just using stations that have at least 50 years of data, um, that, it's just this incredible across the board increase. Now, a little bit of the over redness of this map is just cartography, right? You've got points on top of points, and so it makes it look more red. But actually, if you look for any yellows, and I mean, orange is kind of moderate change, yellow is very low change. There's very little low change. There is some, just a few out in Russia, but it's pretty remarkable. And a little bit one on the UK, or the UK and Ireland, but generally, like across Europe, you just see this, incredible warming over just the last 60 years, right? And so this is not Fahrenheit either. This is centigrade. So this is like 5 to 6 degrees sort of warming across Europe. And, Germany has this incredible density of stations compared to the rest of them. But, and then of course the Arctic nations are in particular experiencing kind of more up there in Finland. But yeah, kind of fascinating, right? So you can kind of start to understand why perhaps the EU has been a little bit more willing when you just have this across the board kind of warming that's apparently very, very obvious. Anyway, all right. So we're talking about forcings and feedbacks in climate science, right? So we've got this conceptual model. We've talked about sort of some of the individual contributions and how conceptually they add to either warming or cooling of the Earth, including the black bodies. And remember, the black body is really just that idealized state of maximum absorption of energy. Um, and it's named black body because darker colors do actually absorb. But what I haven't mentioned yet too is it also has the idealized potential to radiate back off that heat or that energy in the form of heat, especially in the infrared and long wave infrared in particular. So that's the idealized black body, right? And so the way that's important here is understanding that it's the surface of the Earth, both the terrestrial and the ocean have black body characteristics, but so do various components within the atmosphere, right? Aerosols, water vapor, and that sort of stuff all have um, black body type properties, meaning they can absorb maybe not the ideal amount or the absolute maximum amount, but they can absorb and radiate back off energy. And we use that theoretical relationship of the black body to describe that. So yeah, we've got this conceptual model, right? And now I want to talk about sort of all the forcing. So we understand the theory behind, why aerosols or why these various things might lead to it. How do we or lead to changes in climate? How do we start to actually model that so that we get temperature influences or whatnot? And so the first thing is to think of the forcing. So the forcing is really just that initial response of radiative changes in radiation at the top of the atmosphere. So we're really just trying to understand what's contributing. So forcing is really just what is contributing to the changes in the climate that we're seeing, the amount of energy in the climate that we're seeing. So when we talk about radiative forcing, we're really trying to disentangle the various components that lead to climate changes. That the amount of energy being absorbed within the atmosphere, and so this is most commonly thought of in terms of the greenhouse gas concentrations, aerosols, solar irradiance. I'm going to go into all those in a minute. So when we think about radiative forcing, we're really trying to say, okay, well, we understand conceptually all these things feed to differences in climate. How do we start to just look at one or another? And to do that, we look at the forcing of each given component of radiation. Basically, if it's increasing solar irradiance, then that's a forcing all by itself, right? And we can isolate that from everything else by holding everything constant and then measuring the impact that solar irradiance increase has on our climate. So and really, we kind of expect this increase in temperature if there's more solar radiation being absorbed or less terrestrial radiation being emitted into space, right? And we expect the inverse, decrease in temperature if solar radiation is absorbed or more terrestrial radiation is emitted into space. These are the kinds of questions that we start to ask, right? We hold other things constant and we say, okay, well, if we just dial up the sun, we expect to see more stuff being absorbed, and therefore we should see warmer temperatures, more energy in the Earth's atmosphere, right? So this is kind of what we do. This is different than feedbacks because feedbacks are really the processes that can potentially amplify or decrease the initial response of a given forcing. So there's lots of these, and I'm sure you've seen these. Sorry about the quality of this. I couldn't ever find a better quality version of this, but I'm sure you've heard of positive feedback loops and negative feedback loops. I'm going to go more into these in a moment, but the one I'm sure you've all heard of is the positive feedback loop of if you increase, CO2, that causes warming in the atmosphere because we understand that gas has the potential to absorb energy and release it back and emit it or hold it basically in the atmosphere. That causes warming. Warming increases evaporation, and we have no shortage of water. So that increased water vapor then goes into the atmosphere and continues the warming. And so you get this cycle of more warming, more evaporation, more warming, more evaporation, more warming. And you keep going and going and going. And so it's non-linear. It's a feedback loop. It's actually, continues to increase. Given that we've did this initial contribution, we could actually just, we could say increase CO2 by 50 parts per million and let the machine go, right? And it would just continue to warm based on this feedback. A negative feedback loop using the same concept actually would be increasing CO2 causing global warming, increasing evaporation, which increases the water vapor, but then increases low clouds. And that actually warms the atmosphere and decreases the amount of warming because increased low clouds increases evaporative loss. Latent heat goes down. So you could actually have a negative feedback loop where it starts to cool down. Then evaporation maybe isn't as big, which then maybe finds a equilibrium. But if you keep increasing the CO2, then you're going to get more clouds and maybe it balances out, right? So that's an example of a negative, though. It's generally decreasing the amount of energy versus the positive is increasing the amount of energy. So let's go into these individual forcings real quick. So CO2, we understand, the thermal characteristics, the heat holding capacity and everything, but it actually does max out, right? So the relative contribution, this is just showing that watts per meter squared. So this is that amount of energy being irradiated off. CO2 has the potential to hold a lot until it hits this kind of hypothetical maximum. And then then the relative contribution of or the addition of CO2 doesn't necessarily meet the increase in temperature like it does at lower concentrations. So, and this is all because of the saturation point. CO2 becomes saturated at a certain energy level, right? You can imagine, this sort of with boiling water. Once it reaches boiling, it doesn't get hotter, right? It's maximized. It's hit its maximal absorption of energy. It simply can't get any hotter. It just changes phases at that point. So CO2 as a forcing, we understand, has this type of relationship. And so because of that, we can plug this in and we can kind of test in a world without CO2, what does the radiative forcing look like? Or at certain concentrations of CO2, what does the radiative forcing look like just from CO2, right? Another one we look at often is methane. And we look at it because methane concentrations have gone gangbusters recently, right? They've just kind of taken off from a number of resources, which I'm sure you all have heard about, right? It's gone from 700 parts per billion to 1,600 parts per billion. But this is parts per billion, not parts per million. And so remember that methane is far less concentrated, for a smaller amount of methane in the atmosphere than CO2, I mean, orders of magnitude, by more than a factor of two, I guess. But but the trick is with methane is that per molecule it actually has more potential to hold heat, and that's because the absorption peak is around 8 millimeters, and you can kind of see it right here. Remember this radiation transmitted by the atmosphere. I didn't focus on methane before because we were more focused on this end of the atmosphere or end of the infrared. But here's methane where it peaks in those absorptions. There's two different peaks. There's one within the solar radiation, right, which is kind of a big deal that actually reflects back off. But this one absorbs that energy and it peaks kind of right here, right where we start to emit. So in general, right, like it's not nearly as big as a contribution to temperature changes as carbon dioxide because it's a lower concentration in the atmosphere, even though it's it's more potent. I've heard up to 25 times more potent than CO2. However, the lifespan of methane in the atmosphere is much less, right? So it only lasts in the atmosphere for weeks to months to maybe years, but CO2 is something that accumulates in the atmosphere for millennia, and that's the trick, right? So we can look at just the relative contribution of methane using this absorption piece, understanding the percent of methane within the Earth's atmosphere, and account for that. So that's another forcing that we can look at. Another one, and this is a really important one, is aerosols. So aerosols, or you probably are more familiar with the term like particulate matter, which is not just PM 2.5 and PM 10, the stuff that we get when we have wildfires, but it's any kind of sort of sulfur dioxide, any of those kinds of things that float around the atmosphere that are that water can bond to, right? Or that has a mass large enough that it can actually reflect energy back out of the atmosphere. So before it even hits the Earth's surface. And that's actually the net effect of most aerosol forcings, is that that it blocks the amount of solar irradiance coming into the Earth's atmosphere. It blocks it up at the top of the atmosphere. And this is a picture from the book, both of these, right, are from the book, but this one is showing the aerosol layer caused by volcanic eruption, right? So you can just see how you start to imagine how solar radiation coming in here kind of hits that wall and just gets reflected back out before it hits the Earth's atmosphere. And so this graph kind of shows the relative contribution. So the solar radiation transmitted, right, percent transmitted, typically around 94%, 93%. But with these various volcanic eruptions, you can kind of see how that blocked it. So in those eruptions, right, you have little, you have dust and dirt, which are big particulate matter and aerosol kind of components. They go up and they block what is coming into the Earth's atmosphere. Right, this really massive one, right, that actually cooled things down significantly for that little period. And then another big one there too. So pretty interesting, right? But look at the lifespan of these particulate matters or these aerosols. In terms of how long it impacts that solar radiation transmission. Even the really big ones, the effect is really only maybe 5, 6, 7 years at most. And so that's another thing to consider with the aerosols is that some of these are very short lived. Even though they have a negative impact, they're negative forcing, meaning they're actually causing less energy to come in. They're cooling the Earth, and all kinds of things contribute to this, right? We actually put aerosols in the atmosphere sometimes for called cloud seeding, right? Where sometimes we're actually intentionally releasing these things so that we can create clouds to counteract the fact that we've completely messed up, climate systems, and we want it to rain again in some places where it hasn't in a long time. We actually go in and do that. But, land uses, all kinds of stuff can create that dust and those particulate matters. And certainly, of course, wildfires can create those particulate matter getting up into the aerosol and then contributing to this net cooling. So that's another forcing that gets kind of taken into effect. The final one, that kind of book kind of talks about, and certainly the final like big one is just solar irradiance, right? And so we do have this 11-year cycle of sunspots, and that's absolutely detectable and absolutely measured and modeled as an independent forcing within the climate system, so that we can kind of figure out. And this is just that graph from the book, kind of showing that cyclical nature, right? Every 11 years, we get these low spots, and that's absolutely something that we can estimate. And it really, like the total irradiance variations equate to about 1 watt per meter squared. So so not a huge component, but certainly a component, one forcing that is considered within these models. And so when you kind of put them all together, this is what you get. And I really like these kind of graphs because it's really like, okay, these are all the hypotheses about the interacting effects of climate, kind of put all into one graph over the modern record. So this is all stuff that we've measured, right? So well-mixed greenhouse gases include CO2 and methane and everything. We call them well-mixed because they're up in the upper atmosphere and there's a ton of circulation up there, always blowing like crazy. So you get well-mixed. So you don't get the super high concentrations in one place versus another, unlike ozone, which is not well-mixed. That's why you have those hole in the ozone layer and over Australia and the South Pole. You have stratospheric H2O, solar irradiance, right? So there's the sun cycles in the orange. You can kind of see those. There's sunspot cycles. So those are accounted for. So that's their relative contribution. Stratospheric H2O is there. It's a very low one, right? Ozone is there. It's certainly, is a small component, but it's certainly there. And then you have like land use. Again, that's a aerosol producer, so it has a net cooling effect. So the effective forcing is, the zero line is right here. So if it's above the line, it's increasing temperatures, and if it's below the line, it's decreasing temperatures, or the forcing. So land uses, right, decreases temperatures because the more we plow and take out trees and burn them up and whatever, it actually puts more aerosols up in the air. But it's only this much, right? Snow albedo, that would traditionally be right at 0, but it's kind of right, like it's we've had less snow cover generally, and because of that, it has a net increase in forcing. Versus stratospheric aerosols, that's really low, right? So these big dips, sorry, are typically the volcanoes or some other, major event where we put a ton of particulate matter up into the atmosphere. We have black carbon here, the black solid line right there, right? And that's the fact that we have carbon dioxide, but then we have like black carbon particulates, and that is coming from wildfires. Typically, it's also coming from just burning wood in general, and that when it gets up there, because it's a black body, it's more closer to the idealized black body state. It's a particulate that actually holds heat while it's up there. So it doesn't just immediately reflect it back out. It actually holds the heat. And so black carbon turns out to be relatively significant, especially recently with all of our catastrophic wildfires, a relatively large contributor and relatively large forcing in the climate system. Versus tropospheric aerosols, certainly decreases a significant amount. And then aerosol indirect effects, which is that bouncing back out. So you put it all together, and you get this really nice picture of sort of what are the competing things driving the potential response in climate. And the key here is that you have to look at the net right at the end. And so all of these things kind of combine. Like the most is sort of reflective tropospheric aerosols, and it's not close to sort of the well mixed greenhouse gases, and that is why we're seeing that overall net increase in temperature. I really like this one too. So that this graph is from Hansen, and if you don't know about Hansen, he is the guy that really like launched so much of our understanding of climate change into the modern era, and produced some of the most widely cited climate science papers out there. He now works for NOAA, and just his papers are remarkable. He put that together, but then the IPCC went a little bit deeper, and looked at it over the last 250 years, and kind of laid out relatively what are the various forcings that we can measure, or that we have good information for, and what is the magnitude of that forcing. And so you see CO2 only having a positive impact, of course. You see the error bars associated with that, right? But the error bars certainly outweigh the relative effect of everything else. So we know CO2 is the big one, right? Other greenhouse gases like methane and nitrous oxides, that relative contribution, the hatch marks, means that there's a relatively high amount of uncertainty associated with it. So ozone both has a negative and a positive effect on radiative forcings. And so, and then you have the water vapor from methane. You have surface albedo. And again, land use is so tricky. It goes both ways, right? But then you have black carbon and snow, and it's just this really nice kind of layout. And again, at the end, they show the total anthropogenic, the total from solar irradiance, and you get this nice net effect. Like, okay, really, like the total anthropogenic is so much greater than anything that would be negating it naturally. This is why we've seen the warming. And it's not surprising, because getting back to feedbacks, we know about all these feedback loops that even if we hold all those things constant, or when we hold all those things constant, we see major contributions. But we know that things don't operate in isolation. We know that there are feedbacks, and so this climate change knowledge .org group is pretty good. I think they're out of the UK. They've put together all kinds of feedback loops if you're interested in checking them out. This one's specifically on the Arctic to kind of get at, right, you have a little bit of warming due to various greenhouse gases that yields summer sea ice melts. Melting sea ice cools the albedo by replacing, right, the snow with dark open water, which continues to increase warming, right? which will just melt those things even more and more and more and more and more and more. And even if you don't continue to increase CO2, once you've started that, you have the potential of just having this positive feedback loop of increasing warmer and warmer and warmer. And they have all these, potential other impacts. And that's just one of them, right? You have the sea ice disappearing, more water, so more heat retention, more irradiation, right? But then you have the wetlands. The more you warm a wetland, the more it's going to release methane, which is a greenhouse gas, right? Even though it's more short-lived. But that will increase temperature, certainly over certain regions. Same with bogs. And again, this says 25 times more powerful, but we know it's short-lived. But it's still, with mountain permafrost, that's certainly methane that has not been part of the Earth system for quite some time. Oops. We have Amazon rainforest, kind of same thing too, right? Increased drought, which increases wildfires, which means more tree dies burn, release more CO2 in the atmosphere. It's not locked back up into the trees, and therefore rainfall decreases. As rainfall decreases, it continues to warm up their surface, which continues to dry out even more, which continues to create more fires. Again, a feedback that doesn't really end, on its own. Same for the ocean. If we shut down if we warm up the water, we shut down the exchange of CO2 to the deeper parts. If we shut that down, that means ocean waters dissolve less CO2 and may even release some. So oceans are actually a sink for CO2 traditionally, right? The organisms in there would take CO2 actually out of the air and lock it up in various things, shells and whatnot. But if you don't have that exchange to the deeper ocean, it's not going to suck it up, and we actually potentially release it. And we release methane from the sea floor for the same reason. If we don't have those mixing events because of too much warming at the top, we shut it down, and that continues to increase the temperature rise. So lots of different feedbacks, right? And the book kind of went through the Planck feedback, which kind of leads to cooling, but then you have more water vapor feedback, and so that leads to warming, and then you have the lapse rate from that water feedback, which it's a quintessential, like, this causes more evaporation. Evaporation causes more water in the atmosphere, which means warming, but then that water forms into clouds. This is the lapse rate, which causes cooling, but then you have ice albedo feedback because of this warming that causes more warming. It's really complicated, right? All of the definitions of forcing and feedback are just not clear cut at all. They're based on existing climate models and all the physics and math and the processes behind them, but it's not clear cut, right? There's wicked little tentacles of things here and there going from here and there, and these relationships sometimes are really well understood, and sometimes they're not understood at very well at all. So lots of uncertainty, and this is that last little section on climate sensitivity, right? Is just that we can kind of with this concept of forcings and whatnot, we can hold back, and we can focus just on one forcing or another. And so for climate sensitivity, we typically think about doubling atmospheric CO2 and estimate how much the temperature would change, how much more energy is there in Earth, basically. But and so when we do that, we come up with 3 degrees Kelvin. But we know that there's all these other things, and so that adds these uncertainty coefficient or uncertainty bounds, and it could be between 1.5 and 4.5 Kelvin. So this is the uncertainty associated with things, and a lot of it is due to the cloud forming feedback that is not uniform, and it's so it's so temporary in time, right? The clouds are not persistent over months or years or anything. It's so complicated to model those cloud feedbacks. And so yeah, you can kind of just see how complicated all of this is. But the important part is that we understand these forcings. We can describe these forcings in the context of what we've observed. From that, then we can start to model things. And so the next week, we're going to really dive into the carbon cycle because that's really, really crucial, obviously. CO2 is part of the carbon cycle. A lot of what we do on Earth is part of the carbon cycle. And so dialing that in and really focusing on that will be the focus of next week.